Well, hello all. On behalf of MITAC, the MIT Activities Committee, want to welcome you to the blacksmithing talk today with instructor James Hunter, part of the MIT Metals Lab. We're thrilled to have James talk about blacksmithing at MIT, such a great and interesting part of the MIT Metals Lab at MIT. Kind of the background of blacksmithing, the future of blacksmithing, and the merging of science and technology and art, which is really the beauty of blacksmithing. So without further ado, James, if you can take us away to the world of blacksmithing at MIT.
Sure. Just okay. Oh, I need to go to the start. Sorry, Marty. There we go. All right. Looks good.
Looks perfect.
Okay, great. Well, yes, I'm James Hunter. I'm a technical instructor in materials science and engineering. I got my PhD at MIT in 2015 and then started this job. And I've been doing blacksmithing for about 20 years in different places. So the first thing that I want to cover is just some basic facts about blacksmithing and some about the facility that we have at MIT. This is an image of most of the blacksmith shop that we have. It's in room 4006, which is just across the hallway from the glass blowing facility. And 4006 as a whole, the whole room, is the Merton Fleming's Materials Processing Lab. Mert is an emeritus professor. He still comes by from time to time to see what's going on. So the left third of the room is taken up by the blacksmith shop. The middle third is a metal casting area, which we usually refer to as the foundry. And then the remainder of the room has equipment for welding as well as for fine metalworking, which is a category that includes jewelry. Some basic information about blacksmithing, just so that we can kind of get all on the same page. Forge is both a noun and a verb. So the room that you do the work in is called a forge. The fire or heat source specifically is a forge, and forging also is the process of hammering or deforming metal. Although the metal is often heated to a very high temperature to make it soft and plastic, it always remains solid during forging. Pouring liquid metal is something that does occasionally happen in the forge side of the room, but generally we use the foundry facility right next door to do that. People also sometimes confuse smithing, which is just another word for forging, with smelting, which is the process of obtaining metal from ore, from rocks. So if you look carefully in this photo, you can see that we have 3 forges and about 6 anvils, which lets us accommodate somewhere between 6 and 8 people at a time, depending on exactly what they're working on. And above the forges is a system of ducting and ventilation that keeps us safe from all of the hot combustion gases. So the forges themselves burn coal and operate by a powerful air blast that comes directly below the fire pot. So just below where the hot fire is in this picture, there's a bowl that's about the size and shape of a medium-sized cooking pot, and it's full of hot coals. Burning coal might seem pretty antiquated, but actually has a surprising number of advantages for blacksmithing. These coal fires are a very, very concentrated heat source. The coal itself is pretty insulating, and generally one of these fires outputs about 22 kilowatts of energy in a volume that's roughly the size of a cantaloupe. You can get to that fire from about 180 degrees of arc in front of one of these forges, meaning that they're really good at heating a small part of a very complicated shape very quickly. And because iron is hard to forge and doesn't stay hot very long when it's at 1000 or 1100 C, this is a big advantage for most work compared to the tube-shaped furnaces burning natural gas or propane that you might have seen in the glass shop or possibly on TV sometimes. So I said that we burn coal, but that isn't 100% true. What we burn nowadays is actually a product called coke, which is made from bituminous coal in a similar way to how charcoal is made from wood. In that process, the bituminous coal is heated and the hydrocarbons and sulfur impurities are removed, so that the coke product that we burn only emits CO2 and carbon monoxide, which creates a healthier environment in the room, creates a healthier environment in the city of Cambridge. We burn about 1.5 tons of coke per year. And if you estimate it out for the number of people that consistently work in there during the course of a year, it's about equivalent to taking an extra trip to California on a jet. So the main purpose of the forge nowadays is kind of involved in 3 main goals. The first one is education. We support a lot of undergraduate classes functioning as a teaching lab. We support research activities, somewhat less than that. Usually those are archaeological in nature or metallurgical, but occasionally other research takes place in the facility from time to time. And the last goal is outreach, which kind of encompasses a variety of different things. There's outreach in a literal sense through our participation in the MIT MRL summer program for Cambridge middle schoolers. Host a number of them doing work in there every year. And also within this category is the kind of support and informal advising that we do for students. We have weekly open hours for students that have taken classes, and it's a good opportunity for them to de-stress, work on something other than PSETs and grad school applications, and hopefully have some good conversations with instructors. So that's what we do in there. The question is why we do it. And for those that have been exposed to it, steel is a pretty remarkably versatile artistic medium, and kind of, for some people, exerts a power and a mystery that's kind of irresistible. It can be as hard as stone, or as soft, similar to lead. You can shape it and move it a lot like a piece of clay. When it's melted, it can flow like water. You can cut it or chisel it like wood. You can polish it to shine like silver, and it costs almost nothing. So it's, I don't know, it's kind of incredible to behold, even after 20 years, when I see it glowing and feel it moving underneath a hammer. It's fills me with wonder and amazement. And that's something that a lot of people feel, I think, when they encounter it. Of course, it is also worth mentioning that iron, in some ways, is kind of an ignoble metal, an ignoble material. It rusts away to nothing pretty quickly in the historical time scale. Metallurgists will often call it a dirty metal. It has also been the metal of choice for disenfranchising Native peoples globally and making war for the past 2,500 years. And nowadays, it's responsible for the production of about 9% of our global CO2 emissions, which is an ongoing problem. The story of how blacksmithing came to MIT is a little bit long and strange. So hopefully I can summarize it for you. If you go back to the earliest days of the Institute and take a close look at the MIT seal, you can see that the manus or hand is symbolized by the blacksmith. And it's really no coincidence that they did that, because it was within the curriculum, even at the earliest stages of the Institute. And if you're not familiar with the history of that time period, particularly the history of technology, you might assume that this was a natural choice because of the ubiquity and importance of blacksmithing at the time. But that's true in some ways and really not true in others. Actually, the mid-19th century was a pretty bad time for blacksmithing in America, as well as the rest of the world. Arguably, the peak of blacksmithing as a craft art was in Europe, maybe 100 or 150 years earlier, depending on whether you consider that peak to be in the Baroque period or the Rococo period somewhat later. I find this peak to be kind of exemplified in the work of Jean Tijoux, who constructed this screen for Hampton Court outside of London in 1700. Tijoux was a French blacksmith who rose out of obscurity only when he came to England, and is notable particularly for completing the entire design, as well as the forging and execution of the works. So by contrast, blacksmiths in the American colonies at the same time were fairly preoccupied with basic survival in a hostile environment. Blacksmithing in general in the US probably brings to mind something more like Longfellow's poem about the village blacksmith under a spreading chestnut tree, rather than sophisticated ironworks produced by advanced, experienced artists. But given the circumstances, iron was really too precious to be used in such a decorative manner as the gate that I just showed. And kind of the resulting aesthetic for colonial ironwork is pretty austere. The War for Independence didn't really help the situation. And by the early 19th century, the artistic tastes were also starting to change to evolve to the preference for the neoclassical. And that's an architectural style that's pretty much devoid of decorative iron. So there wasn't a super strong craft tradition of ironworking in America to begin with. And the unrelenting pressure of the Industrial Revolution, the War for Independence, and then the American Civil War kind of squashed what little there was. So coming to the very beginning of MIT, the craft tradition of ironworking was pretty dead in the United States. It didn't stay that way for very long. So this photo shows MIT forge space as it was in 1896 when it was across the river in Boston. And by that time, the outlook for blacksmithing in America was already quite different. This photo is kind of incredible. Every time I look at it, I see new interesting tidbits, and it reveals a lot to the trained eye. One thing that is particularly striking, I think, is how modern the space looks. If you compare and contrast this to the photo of the forge that I showed at the start of the talk, it's really not that different, even down to the ventilation and ducting and everything else. Although they had a little bit more room then than we do now, but it's not too surprising. And it's really not too surprising either that that it was so relatively advanced, I suppose, just because Boston and MIT were on the forefront of technology. Boston was also a fairly cosmopolitan city, I think it's fair to say. And so it's not too surprising either that the arts and crafts movement, at least the version in America, also got its start here, more or less at MIT. The movement, for those that are familiar with it, had begun in England and Scotland some decades earlier, mainly as a response to the banality and oppressiveness of industrial manufacture, and also as an outgrowth of the Romantic art movement and Gothic revival artwork. The first society meeting for the movement took place in the US at the MFA in 1897. So that's a year after this photo was taken. And the first craft exhibition took place later that same year at Copley Hall, which was part of the MIT campus in Boston. So I wonder, looking at this, if any of the people in this photo went to that, if they were still around and still in the city. And it's pretty incredible to think that in 1896, blacksmithing would have been seen, at least to some extent, as an exciting novelty. But the proof is kind of in this photo itself, given the nature of photography at the time being fairly difficult and involved and probably expensive. You know that there's nothing casual about the fact that this photo was taken. It's a portrait, and these students were excited to be in it. And it's meaningful that this is the activity that they chose to represent themselves in 1896. And also again in 1898. And I laugh when I look at this because it's really not so dissimilar from a lot of the photos that the students take of themselves when they're in the forge space nowadays, I think. So the revival movement continued for a while. Blacksmithing remained in the curriculum at MIT up until about 1940. And as best as I can put together, the fact that it left in 1940 was probably a casualty first of Carl Taylor Compton's curricular reforms, which took place in the 1930s. And they were combating the idea that MIT was more of a vernacular school. And then following that, there is, of course, the lead up to World War II. And the craft revival that MIT had helped to participate in also had petered out at around the same time, giving way to modernism. So although it was predictable and probably inevitable, the mind and hand had sadly lost a little bit of the hand. The fires were cold and the ringing of anvils was gone from the halls, but only for about 44 years. A second American craft revival had begun in the 1970s, and ironwork was starting to come alive again in spectacular new ways and old ways that are, I think, typified by this famous work by Albert Paley, who we were lucky enough to have come and lecture here a few years ago in our Metal Arts lecture series. And it's interesting that when Paley got his start, he was actually a trained jeweler and didn't really have any formal training in ironwork at all. And this was more or less the first thing that he made. I think at that time, there weren't a whole lot of people left around to learn from. So Sort of against that general backdrop of increasing craft revival and craft knowledge, Professor Emeritus Sam Allen put together a single, fairly rudimentary forge in Building 13 in 1984. He was helped by a pretty considerable loan of equipment and expertise of Sadie Forbes, who's on the right in this photo. Sam also started a blacksmithing first year seminar the same year, which has run every year since then, including last year, although we were obligated to live stream all of the blacksmithing demos, and there was a real missed opportunity for them the students to do work themselves with their own hands.
Hey, James, we
Yep.
have a question.
Sure.
What did the students do for hands-on experience with metal properties while there was no forge?
Oh, you mean in the period of, say, 1940 to 1984?
Mm-hmm.
That's a really good question. I know that there was a major shift in that period away from vocational work. So I imagine there still would have been shops around where they could work in order to build apparatus and so forth that they needed for what they were doing, but it would have been more machining related rather than forging related.
Mm-hmm. Great, thank you.
Okay. So pretty quickly after that point, there was an expansion of the forge to 3 forges, 3 fires. And that took place as part of a renovation that included the glass slab. This was a huge improvement, notably because it allowed blacksmithing to be way more accessible to the Institute through IAP classes, which had first been offered in 1987, but that first January must have been pretty dismal in Building 13, huddled around one forge, I would assume. I have to ask Sam about that sometime. And in this photo, I'm showing the MIT 150 tour in 2011, which shows the glass side of the room. So in this photo that we took in 2014, we've kind of recreated the 1898 portrait. And certainly a lot of things have changed since then. But some of the most significant changes have been to the demographics, I think. This photo was taken just before I graduated in January 2015. And one of the reasons that I took this job, and one of the things that I like about it the most now, is that it allows me to teach blacksmithing to a lot of students who ordinarily wouldn't get exposed to it and possibly don't fit the image of a stereotypical blacksmith in one way or another. Blacksmithing in America has a lot of the same problems as other aspects of American life, and it's gratifying to be able to make a difference in our small way, one seminar and one IAP class at a time. So bringing us up to the present day, one of the most significant changes that we've had is the renovation that took place in 2015. And as I mentioned earlier, the room is the Merton Fleming's Materials Processing Lab. And the funding for the renovation came primarily from a lot of Mert's old students. But to honor Sam Allen's role in bringing back blacksmithing to the Institute, we created a sculpture that kind of echoes the Manus portion of the MIT seal. And this was mostly created by Mike Tarkanian, one of the other instructors in the space. And I think I helped with maybe 10% of the total amount of work for this particular sculpture. And this was enormously beneficial. One of the main things that it allowed us to do was significantly expand the IAP offering. We're now offering that to 54 students every January, with the exception of this January, because we're simply not able to do it given the circumstances, which I think is probably the first time since 1987 that it hasn't run. The reason why we're able to expand is not because the blacksmithing space got larger, but really because we were able to separate from the glass lab. They have a very busy schedule as well. And after that many years of being in the same space, I think it was time for us to move apart a little bit, and we get along much better now after that. This shows some of the IAP classes in progress, and you can see that there's quite a bit of action going on in this shot. Lots of people working all at once. These classes typically run from 1 p.m. to 7 p.m. 3 days a week during the whole of January. Now I just want to go through a few of the things that have been made in the space. And unfortunately, a lot of these things are things that I have made personally, just because I haven't done a great job of cataloging the student work since I've been here. But I was planning on making a change in that respect this January, but unfortunately, that wasn't possible. So there's a great variety of work that's made in the space. A lot of it is in the form of small figurines. These are fairly traditional in their scope. Things like dragon heads and gargoyle heads are typical of sort of Gothic revival type work. The octopus here is maybe a little bit more modern in its design, although the methods used are pretty identical to those in the previous examples. The tavern puzzle on the right here is an example of student work, and it does actually work, which is great. It's a good project, because you have to be very, very precise in your work in order to get it to function as a puzzle. We've also made quite a few tools, and some of the advantages to having the facilities next door for fabrication and large-scale heat treating and so forth are that we can make things that are much larger than we would have been able to make in the past. These are both examples of tools that would be used for making European plate armor. And this is something that's been sort of in demand over the past years that I've been here, but we haven't ever had the equipment to actually make it. And I'm interested now that we do have it to see what students will do with it. We also make a large number of tools and fairly complicated forgings. So the image on the left is a fairly standard blacksmithing tool that is pretty difficult to make yourself, but is relatively easy to do with the equipment that we've accumulated in the new space. The image on the right is a 1950s style ice axe, which is probably one of the more complicated forgings that's been made in the space, and kind of highlights what's possible in terms of complexity and performance. So moving on at this point to talking about some of the coursework that we support in the space. And mostly that is archaeological coursework, and specifically class 3094, which is Materials and Human Experience. That class is affiliated with Professors Heather Leckman and Dorothy Hosler, who are in the Material Science and Engineering Department, specifically in the Center for Materials Research in Archaeology and Ethnology. These images show work from the first unit of that class, which focuses on ancient Indian metallurgy. The first photo shows a smelting process which the students undertake. And this involves taking copper ore, which is gem quality malachite in this case, and heating it with charcoal in such a way that it gives up the copper metal that it contains. And it shows a before and after of the ore and the metal that it produces. The second two images are related to a forging process that the students do in the class, where they first cast a metal ingot that is 75% copper and 25% silver. So metallurgically speaking, it's a sort of bronze. They do this casting themselves, which is very exciting and involves a great deal of safety equipment and protocols. The ingots that they produce are fairly similar to the ones on the right, and they start off kind of a bronze color. And through a series of forging and acid etching steps, they eventually reveal a highly enriched and shiny silver surface, which was a technique that was favored by a variety of peoples of the ancient Indian region prior to European contact. This is from another unit in the same class. Typically the second half of the semester is a variety of different projects. This one focused on Indian smelting furnace technology. And it really highlights the utility of that space, not just for traditional forging, but for any type of lab work that needs a lot of space, generates a lot of mess, or involves combustion. The last image that I'm going to show from that series is on the several of the Mayan murals that we've recreated in 3094. And you can actually go and see these for yourselves, assuming you have access to building 16 someday. Again, be well if you don't now. And these are up on the 5th floor. And these are recreated murals from two different periods of Mayan history. The one on the left is from approximately, I think it's from approximately 1,000 years earlier, but I may be misremembering that exact detail. And you can see that there's a considerable evolution in the kind of design motifs and use of color. I particularly like the image on the right, the kind of fantastical creatures from the Mayan mythology were especially appealing to the students, I think. So to highlight some of the research that is done in the space. I'm going to talk about one particular example from a class that we run 3042. This is the kind of capstone engineering class for material science students. And the way that the classes run these days is the students take the semester to do basically what amounts to original research on a particular project, and come up with some kind of engineering solution or what have you to that project. This particular project was focused on investigating a phenomenon called carbide banding. And this is, in modern days, generally considered a problem in steel production. Steel is made up of iron and carbon at its simplest level. And sometimes when you're producing steel, you end up with a situation where the carbon is not exactly homogeneous and it's present in the form of bands. It's also the primary phenomenon at work for producing the kind of incredible patterning on the legendary Wootz Damascus steel daggers and blades that were produced in the Middle East and elsewhere prior to the 18th century. If you're familiar with Damascus at all from modern production, it's a fairly different process. In modern times, usually you achieve this by layering dissimilar metals. So this was a fairly sophisticated project. We had to produce a lot of custom steel alloys. It's forging the ingots successively in terms of increasing the number of cycles, as you can see in the GIF below, as a necessary step. As that number of cycles increases, you can see the relatively disordered carbides in white gradually becoming more aligned. And it also involved some reasonably sophisticated computer simulation and taking advantage of a lot of the computational resources that we have available at MIT. Students use the Abaqus finite element simulation software to try to understand to what extent random distributions of particles through a forging process become aligned or not. And their preliminary results was that simply deforming an ingot doesn't lead to any increase in banding. So the mystery is still has some potential in it. So this more or less describes the forge up to the present day. And so far, we've kind of seen how the space fits into high-tech education, research, and advising objectives. And now I want to take a few minutes and kind of talk about how technology fits into modern blacksmithing and how we can take advantage of some of the unique tools, the unique environment that we have for creating art at MIT. So you've probably gathered from what I've said that technology and blacksmithing have had somewhat of a complicated relationship. And it's certainly true that the pressure of the Industrial Revolution did help to destroy the ironworking craft tradition, both in the United States and also worldwide. But at least in the early days, this wasn't guaranteed to be the case. And if you recall the Hampton Court gates that I showed earlier by Jean Tijoux, the main characteristic of these works that distinguishes them is the incredible use of leaf work. All of the gilded leaves are iron, very thin iron sheet, maybe 1 millimeter or 2 millimeters thick. And especially in the later Baroque period, this was greatly enabled by the invention of a piece of technology, which was the rolling mill that was capable of producing thin iron sheets, which took place around 1690 in England. And certainly this type of thin, delicate leaf work that embellishes this gate took place prior to the invention of the rolling mill, but you would have had to produce each thin sheet from a larger iron bar just by laboriously hammering it out before you could then cut it and form it into a leaf shape, which maybe is a little bit like having to first weave the cloth before you can sew it into a jacket. Now, the analogy that I'm trying to draw here is that adjacent to the forge are facilities that allow us to cut two-dimensional shapes and three-dimensional shapes from sheets and blocks pretty rapidly and assemble those shapes in a pretty arbitrary way. The past several millennia have certainly established an artistic idiom for steel, that its beauty mainly lies in its plasticity, graceful curvature, the texture that you achieve through forging. And synthesizing these resources allows us to create both within that idiom with comparative ease, as well as beyond it. I think that we can realize new ways for iron to be beautiful that our forebears could not possibly have imagined and would have been difficult or impossible for them to achieve. Now, this is certainly not a new idea, and it's really embedded in the working methods of people like Albert Paley and perhaps Alexander Calder and other men and women. But I think achieving it in the way that I'm imagining describes somewhat of a change in outlook and education. And to explore this and just kind of see what's possible, I have proposed a 4-credit HASS subject on this kind of technology-enhanced architectural ironwork. It's slated to be for this fall, but it kind of remains to be seen whether it will be this fall or the fall after, given the circumstances that we all find ourselves in. And this is a lot like applying the tools and methods of modern engineering to ironwork in a similar way that it was done for architecture and continues to be done in architecture, ironwork being sort of a subdiscipline within architecture. And I'm pretty excited to see what the students in this class eventually create when it finally comes to pass. Some of the images in this slide kind of show the tools as well as the possible results. So on the left, there's a block that's been CNC milled. The middle photo shows a water jet cutter, which can cut a pretty arbitrary two-dimensional shape out of even thick steel in a matter of minutes. And on the right is an example of a leaf blank on the top, which is very similar to the same ones that would have been used in one of Jean Tiju's screens or gates, except that it was cut in a couple of minutes instead of the several hours that it would take to chisel that by hand out of a sheet. And below it is that blank forged into a leaf. This is another kind of test piece example from this sort of logic of working. So this is a kelp frond in iron. And this particular example went from the drawing stage, two-dimensional computer drawing, to the finished kelp frond in a couple of hours, which I think is pretty incredible. So these ideas that I'm talking about are certainly not new, and they're also not new in materials science here at MIT specifically. I'm really indebted to Tara Fadenrecht, who is a lecturer in materials science, or actually, yes, lecturer in materials science and engineering. She created her own HASS subject several years ago, and she's been a very valuable mentor as I've been working on creating this class and envisioning the process on my own. I also have to thank Mike Tarkanian and City Forbes, and of course, Sam Allen, who have all been really instrumental to the Forge here at MIT, as well as my own learning and development. That's all I have for this talk. So I'll be happy if there are any more questions.
We don't have any questions at the moment. I think we'll give it a minute to see if anyone wants to drop any questions right in the chat. But in the meantime, yeah, thank you so much for a great talk, James. Oh, and you know what? There is a question here. When do they opt for the machines in the Forge rather than the hand tools? There was a picture earlier on the Damascus steel slide that looked like a machine doing the work of hammering.
Yep. So that's a power hammer. It's a relatively small one, if you can believe it. Although when it's running, you can still feel it on the floor above and the floor above that, and actually the floor above that too. And the Dean for Student Life is right above the Forge, so we typically only run that after hours. So the main distinction for when you're going to go to some kind of powered device like a power hammer or a hydraulic press is when the work gets large and when the work isn't very complicated. They're definitely blunt instruments. If you have a bar that's maybe bigger than an inch in cross section, you're going to have a pretty difficult time forging that down by hand. And that threshold is obviously something that's going to be different for people of different sizes and strengths.
Mm-hmm.
One of the great things about these tools is that they are a little bit of an equalizer in the sense that you don't have to be large and muscular in order to achieve the same results.
Great, thank you. Well, it looks like that is it for our questions, unless Fufi might be adding in one more. But oh, here we are again. Are there any blacksmithing examples from the MIT Metal Labs that are highlighted around the campus?
Interesting. So if you go by the Forge in the glass shop, there is a case of that shows student work over the years. But as far as I know, that's the only place around campus that specifically highlights stuff that was made in the blacksmithing shop. The main problem here, and this is a problem too for kind of cataloging the work after the fact, is that all of the best stuff that gets made in the Forge ends up leaving with the students that have made it.
Right. Yeah, that makes sense. How often do people opt for more traditional styles of metalworking at MIT versus something more modern, like the works with Gothic revival designs versus the octopus?
I would say that it's heavily towards the modern side of things.
Mm-hmm.
But more than that, it's heavily towards the more practical sides of things. So most of the projects that students are making, I wouldn't call art with a capital A. It's things more like a barbecue fork or a bottle opener or that kind of things. Although we've had some really incredible sculptural work that has been done. There's usually maybe one or two pieces every IAP out of 54 or so students
Mhm.
that are really first rate.
Great. Okay, well, it does look like those are our questions for today. So thank you, James, for such a great presentation.
Yeah, I hope it was illuminating. Oh, and once things get back to normal, certainly feel free to come by and poke your head in.
Thank you again so much, James, for such a fantastic talk today about the history of blacksmithing at MIT. It's so amazing to learn about it. MIT is amazing.
Oh,
And
yeah.
yeah, for sure. And one of the treasures of Building 4, along with the Glass Lab. So thank you. Thank you again. A great bringing together technology, art, and science.
Yeah, thank you for the opportunity.